Okay, now we're going to go over the first law of thermodynamics using a control volume analysis. Recall that the first law of thermodynamics states that the time rate change of energy into a system is equal to all the heat in subtracted from all the heat out plus all the work in minus all of the work out. And in your thermal class, you probably saw it written like this: is this equal to Q dot minus W dot, where the work is assumed to be going out of your system and the heat was assumed to be going in. Okay, just remember that if you guys work with physicists or chemists, both the work and heat are assumed to be going in. And so they just use a different nomenclature. To me, that one makes more sense, but engineers like computing work out to do useful things. So they think of work out being a positive number rather than a negative number. Okay, and then in this equation, the energy of the system is given by the integral of over the volume, or the control volume, I should say, or a volume of density times an energy per unit mass, and that energy per unit mass is given by the internal energy plus the kinetic energy plus the potential energy. Okay, and so this is really no different from what you've used in your thermodynamics, except for it's probably a bit more formalized because the energy contained in your system is now a very formal integral. Now we can use the RTT on this because we have a time derivative here, and that is appropriate for following a system around in space as it sort of moves around. You could imagine throwing a baseball into the air, and if you want to compute the rate of heat transfer to that baseball as it's moving around, you could certainly do that. Now, if you want to use this for a control volume form, you need to use the RTT, or the Reynolds transport theorem, to convert this derivative to one that is appropriate for a control volume. And so just recall that from the RTT, we have the time rate change of any quantity n in the system is equal to partial t of rho eta in the control volume plus the net flow of eta out through the control surface. Okay, and now we can compare n and eta for our first law, and we can see just by comparing this to this, that to make this integral equal to this integral over here, you can see that eta has to be the energy per unit mass. Okay, or in compressible flow terms, this is the total energy. Okay, and it's called total energy because it includes the kinetic, the potential, and the internal energy. Okay, then from the first law, we have the time rate change of the energy in the system is then equivalent to, in control volume form, using the RTT to convert this time derivative into an equivalent for a control volume. This is equal to the time derivative of the integral of rho e dv in the control volume plus the net flux of E out through the control volume plus the sum of all the work and heat in and minus the sum of all the work and heat out. Okay, and so this would be appropriate for a control volume that I have sort of sketched right here, where we have a generic blobby control volume like this, and the edge should be dashed if I was being really picky. But in this control volume, we are conserving energy, and you can have flow going out through the surface that is carrying mass and energy out with it. and you can have shaft work going out, you can have heat going in, you can have heat going out, and you can have work going into this control volume. Okay, but even though this equation looks quite a bit, it actually looks somewhat different than the first law you used in thermodynamics. It's actually identical. We just got to start working with this a little bit to transform it into a form that you will start to recognize. And just, I say usually, this Q here is just Q dot minus W dot, because again, because positive work is assumed to be going out for engineering thermodynamics. But I prefer just to write it as work as heat in minus heat out plus work in minus work out. Then you can use any convention. You can use any sign convention that you choose. Okay, and so now we'll talk a little bit about heat. You learned more about that in thermo than you wanted to, and you'll learn way more about that than you probably ever wanted to in heat transfer. Okay, and so heat is defined positive into the CV. So Q in is positive. If there's no in, it's just it's assumed to be in. And this heat can come from heat conduction, which you'll learn in your heat transfer class, thermal radiation, which you will learn in heat transfer class, when that is EML 4140. It can come from wall heaters, etc., even combustion. Okay. Then there's also work, and that takes a little, and we're not going to work with heat too much except to find it. But in heat transfer, you will actually learn how to compute heat given the temperature of your system and the temperature of your surroundings. You will learn how to compute that Q dot. And so now we're just given, for these problems, we'll be given a Q dot, or we'll have to find a Q dot. But in heat transfer, you actually learn to compute what Q dot is. Okay, so now work is positive for work done by the control volume to the surroundings. So that is positive work goes out. And remember that for engineering, the W dot is positive, leaving the control volume and removing energy from it to do useful work to the surroundings. And for a flow, work can come from various various effects. Work can come from pressure. Viscosity can do work. There's shaft work, and there can be some other forms of work. Like say if you have a heating element and electrical resistor into your control volume. Well, if you draw the control volume right here, this is actually work in, not heat in. Okay, so you can have electrical work, things like that are going into your control volume. Remember that to tell the difference whether it is heat or work, recall heat is exclusively caused by a temperature difference between your control volume and the surroundings. Okay, and so if there is energy crossing the control surface and it's caused by a temperature difference, and that's heat conduction, radiation, convective heat transfer, things like that, then it is heat. If there is energy crossing a boundary and it is not caused by delta T, then it is defined to be work. And for the first law, it makes no difference as to whether it is heat or work, because energy is energy as far as the first law is concerned. But then you get to the second law, and then you need to keep careful track of heat and work, because the second law cares about the quality of the energy that is being transferred. Okay. And so now for the work, we will sort of work with these two here in this class a bit. Focus mainly on the pressure work. The viscous work and viscosity is more of a sort of grad level thing. So I'm just going to highlight a few points about that. Okay, and so now pressure work. You could imagine we have our system boundary here, and we have a surface patch. Okay, and so now we want to find the work that is done by pressure due to fluid flowing through our surface. Okay, and so we have n hat pointing out, we have pressure pointing down, and we have some fluid flow going out through it, and this is our patch of size dA. And so what is the differential amount of work that is occurring in this control volume? Well, work is defined to be delta W. And recall, I'm using delta because work is an inexact differential. And work is defined to be force F dot displacement. And now we don't care about work. What we care about is the rate of work, or W dot. And so eventually we're going to have to take a time derivative of this. Okay? And so work is a force, and ds is a displacement. Now we have a stationary patch and fluid moving through it, so we need to convert the standard definition of work into something that we can use for a fluid crossing a boundary. So you could think that W dot then is the limit as delta t goes to 0 of delta W divided by delta t. Okay, so we then substitute in delta W over here and stuff it into there for there. So that's just equal to F dot ds divided by delta t. Well, I'm going to move the delta t underneath the delta s, and notice that the limit as delta t goes to 0 of ds over delta t is nothing more than the velocity. And I think this is a derivation that you guys have seen quite a bit in your physics classes before, so this should be nothing earth-shattering. So as the limit as delta t goes to 0, this ds dt is just the velocity, and so the rate of work is just F dot v. Okay, and so now in this little patch, the rate of the work is just force. Is the force vector acting on it dotted with the fluid velocity. Okay, so now let's find the force, and we're assuming pressure. So our force is just minus p times n hat times the area, which is dA. Okay, so then for pressure acting on our surface element of dA, the differential amount of force acting on it is just minus p times n hat times dA, because remember, the pressure always pushes against the surface. Okay, so it is acting opposite of n hat, and that is equal to. Which implies that the differential amount of work, the amount of work acting on the small patch due to pressure, or dw dot p, is equal to the force, which is p times n hat times dA dotted with the fluid velocity. Okay. And now this is into the control volume. So we could then say that to put this in the traditional engineering fashion, so this is actually work out. And so if you want to define it in the traditional or this is work in, I should say, if you wanted to put it in the traditional work in the engineering form where the work is out, you need to flip the sign. And so that work out is just p times n hat dv. And this is just the rate form of p dv. Okay, and so that should be so that should be fairly, you have seen something like this before. Maybe not this formalized, but certainly in thermo you've seen it. Okay, and this acts on the entire control surface. So if you want the total amount of work due to pressure, you just got to integrate that over the surface. So W dot P is just the integral over the control surface, not the area, of dW dot P. And that is in turn equal to the integral of PV dot N hat dA, and that is equal to the amount of work out of the control volume. Okay, and so that is what our work is, and again, that's acting over the control surface. Now, so we've dealt with the pressure work. We can do the same thing for the work that is due to the shear viscosity. And so recall that the viscous work then we can define very similarly, and I'm just going to go straight to the definition. I'm not going to go through the hand-wavy derivation of it because this is it's actually a little bit more complicated. Where tau is the viscous stress. This is a tensor, and yeah, we need to do all kinds of things to get this to work properly. Okay. And actually, that's actually not quite right. Tau dot V dot N hat dA is actually what that is. Okay. And so, yeah, do not worry about this. It gets fairly complicated, but you just need to know that the work due to shear stress is just the viscous stress tensor dotted with the velocity, and a tensor dotted with a vector gives you a vector. And to turn that into the total amount of work, you need to dot that with you need to dot that with the unit normal or the direction of that work. Okay, so then we got this differential patch dA, and we have all the viscous forces working or acting on it. And so we got the shear force, we got the normal stress, and actually, yeah, we got the shear force, we got the normal stress, and we got to dot it with not just n hat, but with all the different directions, because you have normal stress acting, normal viscous stress acting in this direction, a shear stress acting in this direction, and you need to consider all of those different works, or all those different forms of work. And in the case of shear stress, just recall that shear stress is defined to be the viscosity times a velocity gradient, and this can be the velocity in the x, y, or z direction, and this gradient can be also in the x, y, or z direction. Okay, and just recall that if the flow is inviscid, you can think of the viscosity as being 0. And notice there is no shear stress, there is no work due to shear stress if there is no velocity gradient either. So that is two ways to have a flow where the shear stress and the viscous work are essentially 0, as if there's no velocity gradients or the viscosity is essentially 0. Okay, and so that also implies that if there's no velocity gradients and you have a uniform flow, which means that the shear stress is 0 for a uniform flow. Okay, now later on in class, we will be assuming uniform flow, but we are actually going to learn how to correct the energy equation to account for the viscous losses in a pipe, or the viscous work that is lost to the flow in a pipe. Okay. And then also the no slip condition holds. So if viscous effects are important, just recall that the no slip condition states that if you have fluid flowing over a solid wall, then the fluid at the very the portion of the fluid that is touching the wall actually sticks to the wall, and its velocity becomes that of the wall. And if that wall is stationary, there is a very high shear stress at the wall, but its velocity is 0. So it doesn't matter what the shear stress is, it's being dotted with 0, and so that equals 0. And so essentially, if you were to pick a control volume, and the bottom of that boundary would go, and that bottom of that boundary was going to cut the surface, there would be no viscous work leaving or entering through this control surface here, because the fluid velocity is 0, and there would be no shear work. Okay, so 0. Okay, so thus, a careful choice of the control volume can eliminate shear work. And in this class, we're not going to go through the exact forms. We're just going to call it W dot shear. And then you almost never work with this. Again, I'm just pointing out that it's there. And for those of you who go on to graduate school and you take a grad course in fluid mechanics, you will be dealing with that a lot more. Okay. So now let's combine our work terms to the RTT version of the conservation of energy. And so that means we have the time rate change of energy in the control volume plus the net flow of energy out of the control volume. I need to CV, not CS. CV, CS is equal to the work done by pressure minus the viscous work, basically minus shaft work that can be going out, minus other forms of work, plus the amount of heat going in. And like I said, in heat transfer, you're going to learn how to deal with that term. And in this class, really, we're going to be dealing with this term here. And W dot other can come from things like pumps or turbines or things like that. That can be adding some energy to your system. And so just remember that positive work leaves the control volume. That's the standard engineering notation. And if I use our relationship that we found for the pressure work, where it's the integral of minus p n hat dotted with the velocity vector over the control surface, I get this expression here, where again, all I've done was I replaced W dot P with our formal work that we then calculated. Okay, now this looks like a bit of a mess, but I'm gonna do a little, almost a little trick here, but it's not a trick. I'm gonna take this term. I'm gonna take this term over here, and I'm gonna move it to the left-hand side, and then I'm gonna wind up combining these two surface integrals because they are over the same surface and they're over the same area, so we can actually combine those two integrals. Okay, so I'm gonna first move the pressure to the left-hand side of the equation, and that's what I did here. Okay, and I change those to CS and CV. Okay, now why did I do that? Well, we can then combine these two integrals here into one, and I've done that. And you have an E plus a rho times E plus P. This should start to be looking something familiar to you guys from thermo. Okay, but I'll expand E before I do that into internal energy and all that stuff. Okay, and so, but first I'll just play some games with E rho plus P. Well, E rho plus P, I'm going to factor out a density. That's just rho E plus P over rho. Then I'm going to write the definition of E, and that should actually be U, not E. Okay, so I have rho times the kinetic energy plus the potential energy plus this quantity, the internal energy plus P over rho. Well, you guys may have seen that before. That's just the enthalpy. Okay, so the combination of these two integrals here is nothing more than it's based on the enthalpy. Okay, so finally, we have our first law for a control volume, and It's just the time rate change of energy accumulating in the control volume plus the net CV plus the net flow of energy through the control surface, and that is enthalpy plus the kinetic energy plus the potential plus the potential energy and minus all the heat going, or minus all the work going out plus all the heat going in. And small e is just defined to be the internal energy plus the kinetic energy plus the potential energy. And this equation may look different than the one you guys used in thermo, but it is really the same one. It's not that it is not any different. It's just that it is much more formalized. Okay, so this version of the first law, you know how to deal with if there's a velocity profile, or you have a non-uniform flow, or you have a time-varying flow. Okay, and so it works. This version works for all of the problems that you used for the first law in your thermal class. It works for steady state, steady flow. It works for uniform state, uniform flow. It works for filling problems. All you need to do is make the appropriate assumptions and basically cross out the terms, and then just do what the math says to do. And you can have a steady state, steady flow problem. If you assume uniform flow, you can actually exactly turn this into, if you have uniform flow over everything, this turns into the exact form that you guys used in your thermodynamics. And we'll be using the energy equation quite a bit after we start pipe flow. Okay, but you guys have used the first law quite a bit in thermo, so I'm not going to focus too much on the first law in this class. Okay, so I'm going to do one quick example just to show how it's used. Okay, so we're going to do an example, and in that example, we have a reservoir here, and we have a piping system with a pump, and that pump is being used to pump water up to a 30-foot elevation. And the flow rate, which I used to call Q, which it is Q traditionally in your fluids books, but I'm calling V dot in this class. So don't get too worried if you see Q's in my sample problems. I used to use Q, but now that's just V dot. So we have two water reservoirs, and this pump is basically pumping water from basically one reservoir up to the other one. Okay, and the elevation difference here is 30 feet, and our pump is supplying 10 horsepower, and the volumetric flow rate is 2 cubic feet per second. Okay, and so and then there will be some heat loss to the there will be some heat loss coming out of the piping system, and we are asked to find what is that, and we're asked to find what is that heat loss. And in this configuration is actually sometimes used. It's where you're basically storing a potential energy by pumping water to a higher elevation by a 10 horsepower pump, and then say later, right? And so when you need lots of power, like maybe in the middle of the day, you will then drain this pump downstairs and then run this and then operate a turbine rather than a pump to help generate power. Okay, and we have a volumetric flow rate of 2 cubic feet per second of the water, and we are to find the power loss due to flow through the pipe. Okay, and so we'll just assume that is in the form of heat. Okay, because that is really what it is, because it's irreversible. You can't do anything with it. Okay, and so we're going to assume several things. We're going to assume that the surface of the reservoir, which could be a little lake or a little pool, is much larger than the cross-sectional area of the pipes. And in this example, I'll actually show you that the effect of that assumption, and why, based on that assumption, you can assume that the surface, that the flow here, or that the velocity here is almost zero, and the velocity squared is even smaller. And we've been using that assumption all the time for the Bernoulli equation, and in this problem I will actually prove it, that it's a justified assumption. Okay, we'll assume incompressible flow, and essentially we're going to use a variant of it where the density is constant. It's sort of water, and the temperature isn't going to change very much. And we'll assume uniform flow at any section in the pipe. We'll assume steady state. And we'll assume that the temperature is the same between states 1 and 2. Okay, which seems to be like a pretty reasonable thing. You wouldn't expect the pump to add too much. You wouldn't expect the pump to add too much of a temperature to the water. Okay, so now we will go through the solution. And so the solution is to use the energy equation in control volume form with some shaft work in of 10 horsepower and a heating rate or not a heating rate, that's why I use V dot, with a volumetric flow rate of 2 cubic feet per second of the water. Okay, so first we will work with the energy equation itself, and then I'll draw a control volume. So first, from thermo, we are assuming that all losses get converted irreversibly to either to internal energy, or in this case, Q dot. Okay, so here is our first law. Well, we're assuming steady flow, so this term goes away, and I'm going to, for the sake of not writing all of these terms 10,000 different times, I'm going to just call this grouping of terms here just some cap H, sort of like a total enthalpy type thing. Okay, and then now we have pumping work going in and we have heat loss going out. So now I'll draw the control volume. For this, we always have to draw a control volume, and I'm just going to draw it right on this diagram here. Okay, so now, so we have water going, we have this reservoir here, we have the water going around, and then energy is being added by the pump, and it's going up to the top portion of the reservoir. So it'd be pretty natural to choose our control volume to encompass the whole reservoir system, something like this. Okay, and so we have n hat 1, n hat 2 through the second reservoir. I'm going to call this here state 2 for the second reservoir, and state 1 is the lower reservoir, and the flow is again going down, around, and up. And at the pump, I have a W dot pump going into the control volume. Okay, and I have some heat losses here that are going out. Okay. Okay, so, and I'm going to choose my datum for the potential energy to be here. So this is our datum. Okay, and so our control volume is quite simple. And for this problem, you could actually solve this problem using this. This would not be an untypical problem for you to solve in your thermodynamics class. Okay, so now, and we're just sort of showing you how you can take this much more general version of the first law for a control volume and then work with it, and then turn it into something that you've used quite a bit in your thermodynamics. Okay, so we are going to work with this. So now we've accounted for all the work and heat going in and out of the control volume. Now, this implies that our energy equation, because it's steady, just turns into the surface, the surface integral of this cap H times rho v dot n hat dA, and that's equal to the pumping work going out, and then minus our irreversible heat losses through the walls of the heating through the thing. So first, I'll do a little aside here, just on conservation of mass. So aside, if we're to use conservation of mass, that'd be a partial T of rho dV over the control volume plus the integral of rho v dot n hat dA. That'll be equal to 0. This is steady, so that goes away. The time derivative goes away. Then this implies that we have, because rho is constant, we can pull that out of the surface integral. That implies that the integral of v dot n hat dA is equal to 0, or there is no, or the net volumetric flow rate through the control surface is 0. That means we have as much flow going in as we have flow going out. Okay, and so this implies that we essentially have two surfaces here, or actually three. So we have surface 1 here, surface 2 here, and surface 3 we could consider to be the sides of the pipe and the reservoir. And I have one more assumption: impermeable walls. Okay. And so this integral, I'm just going to integrate this over all of the faces. And we have some v1 dot n hat 1 over area 1 plus some v2 dot n hat 2 over area 2 plus the sides. Well, the sides are just the tube walls. Those are impermeable, so we do not need to worry about those because that's impermeable. Okay, so that's impermeable. So we don't need to worry about the sides. And we note that basically the velocity vector 1 will be some v1, since it'll be going down, will be some v1 minus v1 n hat 1, and since the second reservoir is being filled, the velocity vector at 2 will be equal to some velocity magnitude at 2 n hat 2. Okay, because it'll be going, because it's, since this surface will be moving up, n hat, and it'll be flowing in the direction of n hat 2. Okay. So then we do that, and we do those dot products. Surface 1, that v dot n hat will just be minus v1 times a1. If we do the dot product thing in your homework, I would expect you to show that. And then this becomes v2, and the second, and the integral over a2 just becomes v2 a2, and this is equal to 0 because we're still working with conservation of mass. Then we can show then that basically v1 a1 is equal to v2 a2, which implies that the volumetric flow rate is the same leaving the first, leaving the lower reservoir as it is entering the second reservoir, and that's just equal to RQ, which is the volumetric flow rate, or V dot. Okay. So now we've sort of found that. This is just a little aside, and now I will work with the energy equation. So we'll do the same thing for the energy equation. This problem is particularly simple. You can just break up the integral right away. In your guys' homework and your first quizzes for this stuff, I still expect you to do the phase 1, phase 2 thing. Okay, so now we're going to break this up into the various integrals. Here we got the integral of h1 rho v1 dot n hat dA, and the integral over area 2 of the same thing, plus the integral over the sides. Well, that's 0 because it's impermeable walls. Okay, that means we have nothing. We have that means we have no flow leaving the pipe, because if V dot n hat is 0 along the pipe walls, then there is no enthalpy or kinetic energy leaving through the pipe walls. Okay, so now then this implies we can start working with phase 1. So for phase 1, this is just like in thermodynamics, where you really need to do good bookkeeping. If you walk around the control volume, completely close the surface, kept track of your mass flow rates and your enthalpies, most of the problems were not too bad, as long as you had sort of a lot of discipline and you worked through the problems very methodically. Okay, so now we can work with our H1 and start crossing out terms here. Well, P1 equals PATM, which I'm going to take to be 0. Okay, and then, but it does not matter. If you assumed a PATM to be PATM, the problem would still work out just fine. And then GZ1, that's 0 because that's at the datum. Okay, so we've already simplified our R cap H into internal energy plus the kinetic energy. Now, we know that V1 is equal to minus V1 J hat. N hat 1 is equal to J hat. That's just based on the direction because that surface is going up. N hat 1 equals J hat. And V1, as I argued before, equals minus V1 N hat 1 equals minus V1 J hat. Okay, so we do the dot product. And we get that is just minus sort of V1, and I use that up here for our conservation of mass. Then we're going to use our fact that A1, or that the area of the reservoir is much, much larger than that of the pipe. And we're going to start working with this. So then we can say that our integral over H, we only need to consider the internal energy and the enthalpy, is equal to the integral over A1 of the internal energy of state 1 plus 1/2 of V1 squared plus V dot plus rho times V1 plus rho times V1 dA1. Okay? And that should actually be minus. Okay? And so this is uniform flow. So we can pull this out. Then we work through the integral here. We have, then you will wind up with just a very empty integral over A1 dA1, which is just the area. And so working through that, this entire this nasty integral here just turns into a minus the internal energy of state 1 plus the kinetic energy plus rho V A1. And and V times A is just the volumetric flow rate, or Q in this problem. And I only half apologize for using two different nomenclatures for volumetric flow rate, V dot or Q, but that is, if you look in different sources, you will find different nomenclatures for just about everything. So that's just something you have to get used to. My old notes used Q. I'm starting to use V dot for everything, and I haven't updated everything yet. Okay, I was planning to, but making these videos takes a long time. Takes a very long time, and so that took a lot more time than I thought. Okay, and then the grouping, as I said before, of V1A1 is just the volumetric flow rate, which we have argued is constant throughout the entire reservoir system. Okay, now what do we do about V1 squared? Because we're not given any information about the area of the reservoir, with the exception that it is huge in comparison to that of the pipe. Okay, well, we can use the fact that basically no matter where we choose our control volume, I'm going to scroll back up, we could choose the control volume to go from here, oops, wrong one, to go from here and then cut into the pipe like that. That'd be perfectly acceptable a control volume. It'd be bad for analyzing the pump in the system as a whole, but if you want to examine the effect of V1, then this is a perfectly acceptable control volume. And if you're to do conservation of mass on this control volume, you would still find that the volumetric flow rate, that the volumetric flow rate here and the volumetric flow rate here is actually the same. Okay, so that means if we're assuming uniform flow, that the velocity times the area is constant throughout this entire piping network. Okay, so this means that if we use if we're to argue that V1 squared is small, we can just make the argument, well, that Q is that for this problem, Q, or the volumetric flow rate, is constant throughout the entire piping system. And we know that the area at the top of the reservoir is much, much larger than the area of the pipe. And so velocity 1 is just the volumetric flow rate over A. I just took this and solved for V. And if A1 is extremely large, then V1 becomes small, okay? Then you could say that V1 approaches 0. It never becomes exactly 0 because, you know, the surface moved down and up a lot. And then if you take a small number and you square it, it becomes even smaller, okay? And so basically V1 squared becomes extremely tiny. And so this means that the kinetic energy is essentially 0, or the kinetic energy is essentially negligible. And so basically we could assume that this is small. And this is an assumption that we made all the time when we're working with the Bernoulli equation. Okay? So the kinetic energy term goes away, and that's only because the cross-sectional area of the reservoir was assumed to be huge. Okay, so thus the integral of the total amount of energy due to internal energy or due to the fluid flow leaving the control surface or entering the control surface through the surface of the lower reservoir just turns into minus the internal energy, or minus the internal energy of state 1 times the density times the volumetric flow rate. Okay, so now for phase 2, we have that cap H2 is just the internal energy of state 2 plus P2 over rho plus the kinetic energy plus the potential energy. Okay, so we are assuming that the flow, or we are assuming that U2 is equal to U1, and that's by assumption. Okay, that we're assuming that essentially there's enough time, because the temperature is the same as states 1 and states 2. We're assuming that there's enough time that as the fluid goes around and up, and both of these reservoirs are exposed to the atmospheric environment, that basically the temperature of the fluid here is essentially the same as it is over here. Okay, so we can assume that the flow is isothermal, and that the temperature at states 1 and states 2 are the same. And if the temperature at states 1 and states 2 are the same, and the pressures are the same, then you can conclude that U2 is equal to U1. Okay. And P2, again, the upper surface of the reservoir is exposed to the ambient environment, and so P2 equals PATM, which I'm just going to take to be 0 for this problem. Again, it would not matter if you assume that P2 was equal to PATM, because for phase 2, the this pressure term is equal and opposite to the same term for phase one, and they would just cancel out. And so you can do the same trick for the kinetic energy, is that that's small, and that's a true assumption because A2 is much larger than the pipe area. Okay, and now here, this is not at the datum, it's at some height Z2. Okay, so then, using our assumptions, cap H2 just becomes the internal energy of state 1 plus GZ2. Okay, and now we basically go through the usual rigmarole of finding V2, which is V2J hat, because that upper surface, the flow is going up into the upper surface, and the n hat is J hat, and then V2 dot n hat 2 is just V2 in this case. So you've been through this drill quite a bit by now. Then we can work with the integrals, and we have the integral of H2 rho V2 dot n hat 2 dA2 is equal to the integral over area 2 of the internal energy at state 1, because we're assuming U2 is equal to U1 because the flow is isothermal and the pressure is the same on both the top and the bottom, plus the potential energy plus rho V2. Then we're assuming uniform flow. So you can take this stuff and move it outside, as we've done 1,000 times. And then this term becomes, it's equal to the internal energy of state 1 plus GZ2 plus rho V2A2. Well, V2A2 again was just Q from conservation of mass. So that implies our area integral over the surface of the upper reservoir is just equal to U1 plus GZ2, that quantity, times the density times the volumetric flow rate. And if you wanted to think about it this way, this is really m dot. Okay. And if we included the pressure term, this here would be the enthalpy, and you'd have m dot h. And so that's exactly what you guys had in thermo. It was basically m dot h. Okay. Now we are ready to put everything together. And then the integral over the entire control surface from the first law is equal to the pumping work going in and minus our heat loss going out, which is what we're trying to find. Then we can substitute in our results for the surface integral. Then this becomes minus rho Q times the internal energy at state 1 plus the internal energy at state 1 plus GZ2 plus rho Q is equal to the pumping work in minus the heat loss out. And we can solve for the heat loss to the pipe. And the heat loss is the pumping work going in minus the work that actually went into increasing the potential energy of the fluid to the second reservoir. So now we stick in the numbers that we were given in the problem statement, and again, this is English, so that is 10 horsepower, and we just do the unit conversions and stick in the numbers. And again, this is the English system, so you need to be very careful with how you deal with the pound force and pound mass and slugs and all that good stuff. But if you're careful with the unit cancellations, you should get a heat loss term of 3.19 horsepower. Okay, and so essentially what this does is this goes into heating the fluid, which in turn is lost to the surroundings as it flows through the pipe. Okay, and so really that's almost 32% of the power of the pump in this case is actually just a complete loss of wasted energy. It's a complete loss. And since the heat loss is irreversible, there's nothing you can do to get that back. You can't really use that to do any useful work. Okay, so now what if we applied a different assumption? What if we assumed that the pipes were very well insulated. But it still took the same. So if the pipes were very well insulated, would it take any more power, or would that help us reduce the pumping requirements to pump that fluid? Well, the answer is no, and I'll show you why. So what if the system was basically very well insulated? Well, if it was well insulated, we could no longer assume that the temperature of the fluid was the same on state one and state two. Okay, we can no longer assume that. Okay, so basically the internal energy at state 2 would be different than it is for state 1 because the temperatures would be slightly different. Okay, and so you can go and repeat this analysis. I'm not going to go through the details. And the only thing that is different is that the integral over A2 becomes rho Q times U2 plus GZ2, because now the internal energies are different, and we can no longer make the assumption that U2 is equal to U1. Okay, so that is the only difference, and Q dot loss is equal to 0. So now in this case, what we'll do is we will solve for the temperature rise. So what is delta T? So what is delta T? Okay, so we're going to go through and if you go through the analysis, you'll have the surface integral. This is equal to the amount of pumping work. So now we go through and work with this almost like you did with thermo. And I'm going to skip the details, but you have the integral over area 1 is no different. I mentioned the difference for the integral over A2, and you substitute those in, and we'll solve for U2 minus U1. So that implies U2 minus U1 is just equal to the pumping work going in divided by the mass flow rate minus GZ2. Then recall from thermodynamics that the internal energy is defined to be is equal to the integral of the specific heat from some reference temperature to our temperature, and you guys usually dealt with if CV was constant, so we'll just assume that the specific heat is constant. So if the specific heat is constant and we choose our reference temperature to be 0 Kelvin, you can say that the internal energy is the specific heat times temperature. Then we'll take this and substitute that in for U2 and U1. So then U2 minus U1 just becomes, it becomes CV T2, and this becomes CV T1, and you can factor out the CV, and this becomes the specific heat times T2 minus T1, and that's equal to the pumping work going in divided by the mass flow rate minus GZ2. Okay, and this here is just delta T. So then we can solve for delta T, and delta T is just equal to this expression here. It's the same thing, just divided by the specific heat. So now if I grab the specific heat for water and I punch in the numbers that we are given for the pumping work and the flow rate and all that stuff, this looks like a mess, but it's not that bad. You just need to keep very close tabs on all the unit cancellations. Again, this is part of why I like doing them on the fly in the calculation, because different terms will have different conversion factors. Because like the pumping work is in horsepower, and this is in this will wind up being feet squared per second squared. So there are different conversion factors for different terms. That's just the way the English system is, and so that's why you need to be very careful with all your unit conversions to make sure they're done properly. So do them in the equation, and you will avoid making silly mistakes. But at any rate, if you calculate that temperature difference, you'll get that delta T is equal to approximately 0.02 degrees Fahrenheit. So this is a very small temperature increase. Okay, but it's a very small temperature increase. But if you calculate m dot CV times delta T, you get 3.2 horsepower, which is the exact amount or our Q dot loss term. And so even though there is a very modest rise in temperature, it is still 32% of the pumping work. Okay, and that's just due to the enormous density of water. Okay, and that also goes to say that if your pool is chilly one day, you cannot turn on your pool pump and expect that to heat the water very much. It has essentially no effect on the temperature of the water. And most thermometers would be incapable of even measuring that tiny amount of temperature change. Okay, and so that's it for energy.